So in this lecture, let me illustrate the moment generating function usefulness to compute the moments through a few random variables. So to start with, let me consider this example. This we already have seen, and we derived the moment generating function. So the moment generating function m of s is equal to 1/2 times e to the 2s plus 1/6 times e to the 3s plus 1/3 times e to the power 5s. Now to find the first order moment, that is mean of the random variable, differentiate with respect to s. Differentiate with respect to s. So d over ds times m of s. I can put m sub x also, no problem, but without x also it is understood in the context. Okay, so if you differentiate once, then 2 times 2 will get cancelled, this one. So that is e power 2s plus 3 and 1/6, it is 1 over 2 times e power 3s plus 5 over 3 times e power 5s, e to the 5s. Now substitute d over ds mx of s equal to 0. So then this is equal to e power 0 1 plus 1/2 times e power 0 plus 5 over 3 times e power 0. So if you simplify this, 1 plus 1/2 plus 5 over 3. So let me consider this is so the LCM you can take and rearrange this. So let me write 6 by 6 plus 3 times, so 3 by 2, no, 3 by 6 plus 10 times 6. So therefore this is 19 over 16 if you do the simplification. The same answer if you do directly here also you can get it, that is e of x equal to summation of x times px of x when x equal to 2 times 1/2 plus 3 times 1/6 plus 5 times 1/3. So this is 2 by 2 plus 3 by 6 plus 5 by 3. Again take again simplify this, then this is going to be the denominator 6, the numerator 3 times, so 3 times 6 plus 3 plus 2 times 10, so it is again 19 over 6. Same answer you can get it. So either you can use this formula or you can use a moment generating function to find the first moment, that is the mean of the random variable. Now let us find the second moment. Differentiate one more time. So d square over ds squared mx of s. So this is 2 times e to the 2s from here. Then 3 by 2 times e to the 3s plus 5 times 5, 25 over 3 times e to the 5s. Right? So now substitute s equal to 0, d square over ds square times mx of s equal to 0, then 2 plus 3 by 2 times e power 0, here also e power 0 plus 25 times 25 over 3 times e to the 0. Then if we simplify this, 2 plus 3 by 2 plus 25 over 3. Now in the denominator make it common value 6, 3 times, so 6 plus 2 times 6 plus 50, it's going to be 60, no, somewhere wrong. This is 9, right? 9 and 65 by 6, somewhere this is wrong actually. Where is a mistake? 2 times e power 0, correct, this is correct. Then 3 by 2 times e to the 0, correct. This is 25 by 3 power 5, correct. So somewhere mistake, let us figure out where the mistake is. So this is like the denominator is 6, so 3 times 3 is 2s are 6. No, this is 12 actually, I am sorry, 12 6 times, and this is 6 times 9 plus 2 times 50, so 59 plus 12 71 by 6. So this is the correct answer. So therefore E of x squared equal to 71 by 6. So what is the variance? This is a second moment, by the way, second order moment. So like this you can keep on calculate a third order moment, fourth order moment and all. So variance of x equal to E of x squared minus the mean of the random variable squared. So this is 71 over 6 minus this one is going to be 19 over it is not 16, it is 6 actually. Here also I did a mistake. 6 19 over 6 the whole squared. Then if you simplify this, you'll get an answer. So that you can do simply. It's a simple mathematical calculation. Now let me take another example. Maybe I'll take Poisson random variable. Poisson random variable. So the probability mass function equal to e to the minus lambda times lambda to the k over k factorial, where k equal to 0, 1, 2 and so on. For this we already found the moment generating function in one of the lecture, so you can refer that. So that is going to be that is e to the minus lambda times 1 minus e to the s. So this is a moment generating function. Now we can use this moment generating function in order to find out the various moments. So the first order moment is obtained by differentiate once and substitute s equal to 0. So d by ds of mx of s, which is equal to e power, the same thing will come, e to the minus lambda 1 minus e to the s. Then differentiate the exponent. So if you differentiate the exponent, the first term will be 0, minus into minus plus, then it is going to be e power e to the s. Okay, so therefore I'm sorry, here lambda will come if you take the differentiation, or else let me do one more time. I skipped one value. So if you differentiate that one, that is going to be 0, multiply inside lambda, then again multiply here. So minus into minus plus lambda times again e to the s. If you differentiate, again you'll get e to the s with respect to s. So this is lambda times e to the s times e to the minus lambda times 1 minus e to the s. Now substitute s equal to 0. So then what will happen? What will you get? Substitute then lambda times e to the 0 plus e to the minus lambda times 1 minus e to the 0. So 1 minus 1 0, so e power 0 1. So this is going to be lambda. Therefore the mean of the Poisson random variable e of x is equal to lambda. So this is the mean of the random variable, mean of the Poisson random variable, and this is also called first order moment of the Poisson random variable. Okay. Now differentiate one more time, then you'll get a second order moment. That we can do very easily. So let me denote the first order moment m sub x of s as m prime is equal to, this is lambda times e power s times e power minus lambda times 1 minus e to the s. So this is the first order derivative. Now differentiate one more times. Because we need the second order moment to compute the variance. So let us find the second order moment. We already know this first order moment, so take the derivative once more. If you take derivative once more, then you will end up with the second order moment. So here I have two functions, so let us do by parts. So let me call this as u and let me call this as v. So uv equal to u dash v plus uv dash formula. Just you apply that. Since lambda is constant, you can keep it here. If you differentiate e power s, you will get e power s times e power minus lambda 1 minus e to the s plus uv dash. So e to the s, then this already we had differentiated, that is going to be lambda times e power s times e power minus lambda times 1 minus e to the s. Now substitute s equal to 0, and by the way this is m double dash of s. So mx second derivative of s, substitute s equal to 0. So this is going to be here I already, this lambda is here outside. So e to the 0 plus e to the 0. I mean directly I wrote the answer, or you can substitute the value and get the result. 1 minus e to the 0 plus e to the 0 plus lambda e to the 0 plus e to the minus lambda times 1 minus e to the 0. Now this is going to be lambda times e to the 0 is 1, and that also e to the 0 1. So plus lambda times that also 1. So this is equal to lambda plus lambda square. So the second order moment is obtained, which is lambda plus lambda squared. So this is the second order moment of the Poisson random variable. Poisson random variable. Now in order to calculate the variance, we need to have this first order moment and the second order moment. So variance of x is equal to expected value of x squared minus expected value of x whole squared. So this is lambda square plus lambda minus the first order moment is lambda, and take square of that, then lambda square will get cancelled, so you will get lambda. So variance of the Poisson random variable is also lambda, and mean of the Poisson random variable also lambda. So interestingly, for Poisson random variable, the mean and variance are numerically same. Because the dimension is different. See, this is, if I say my random variable is in meter, then this is meter squared unit is, and this is meter. So numerically they are same, but dimensionally they are not same. Mean and variance are numerically same. When I say numerically same, that means the numerical values are same. Suppose if a lambda equal to 4 means variance equal to 4 and mean equal to 4, but the units are different. So mean equal to lambda and variance equal to lambda. So interestingly, sometimes it happens only for Poisson random variable. Of course, the Poisson random variable lambda is positive. It is non-negative random variable. It is greater than 0. And one more point is, for example, if x is in meter, then what is the unit of variance? Variance equal to meter square. Therefore, variance of x is equal to lambda meter squared. Similarly, for mean equal to lambda, but the unit is in meter. That's it. So the unit is different. That is the point I want to stress here. So numerically they are same, but unit wise they are different. So the variance has a unit of mean square, and the mean has the unit of, the variance has the unit of meter squared, and the mean has the unit of meter. That's the difference. Now let me take one more example. Let's say binomial random variable. Okay, in binomial random variable, let me denote b of n comma p. These are the parameters n and p, and the probability mass function of the binomial random variable is given by n choose k times p to the k q to the n minus k, where k is equal to 0, 1, 2 and so on up to n number of trials. Now let us find the mean and variance using the moment generating function. So for this, first we need to find the moment generating function. So m sub x of s is equal to expected value of e to the sx. So this is summation over e to the sx times n choose k p to the k q to the n minus k, where k equal to 0, 1 up to n. Now let me rearrange this. Summation n choose k, then now instead of no k, I am using the random variable here x and here k. So let me write in one form. So here the running variable is not x, it is k. So let me write k here, and k equal to 0 to n, and I can use either x or k, it's not an issue. Okay, it's after all a dummy variable. So e to the sk, then p to the k times q to the n minus k. You combine these two guys. See, actually this thing is going to be e to the sx actually. So since I have chosen this variable k, and here also k, and here also k, I am changing this s to s is replaced by k, so nothing else. Okay, don't get confusion, it's a dummy variable. So instead of writing summation dummy variable x here, I am using k, that's it. So k equal to 0 to n. Now this one, summation k equal to 0 to n choose k, then e to the s times p whole power k times q to the n minus k. Now let me call this guy as a and this q as b. Okay, so let me call e to the s p to be a, and q to be a. So in that case, this is going to be summation over k equal to 0 to n choose k times a to the k b to the n minus k. Now if you substitute k equal to 0, 1, 2, 3, then this whole thing I can write as a plus b whole power n, whole to the n. So what is a here? A is e to the s times p, plus what is b here? Q whole to the n. So I can write like this. So the final answer is going to be, my moment generating function is going to be this one, mx of s equal to this one. This is a moment generating function. So in order to find the mean of this random variable, let us differentiate with respect to s once. So mx of s prime equal to n times e to the s times p plus q whole to the n minus 1 times, differentiate one more time the inner terms. So you'll get e to the s times p plus 0. So because you have two terms, so you need to do it by parts. Now substitute s equal to 0, m prime sub x of 0, then it is n times e to the 0 times p plus q, and here this is n minus 1 times e to the 0 times p, and look at here, e to the 0 is 1, p plus q is 1 power n minus 1, and n minus 1 is an integer, so it's 1 again. So this is going to be n times 1 times p, so this is np. Therefore the first order moment e of x, that is denoted by mu sub 1, which is equal to np for binomial random variable. Binomial random variable. Similarly, take the derivative one more time to get the second order momentum. So m double prime of s sub x equal to, so here you get this p is constant and this n is constant, so you can take np, then e to the s times e to the s p plus q whole to the n minus 1. Now this is first derivative. Take the second derivative. This is np is constant, you can keep it aside, and again do it by parts. So uv equal to u dash v plus uv dash. U dash v again e to the s, and this is going to be n minus 1 times e to the s p plus q whole to the n minus 2. Again, if you differentiate inside, then e to the s times p plus 0. So where is it going? This is okay, no, this is u, and this dash is v. Let me write one more time, I confused. See, u dash v, so e power e to the s as it is, then this is e to the s p times plus q whole to the n minus 1, this is over, then plus you write as it is e to the s, and the derivative of the second component, this one. If you take derivative, n minus 1 times e to the s p plus q times n minus 2, and derivatives, take the derivative of these guys, so that is going to be e to the s times p plus, if you take the derivative of q, then it is 0. That's it. So m second order derivative, substitute s equal to 0, then np e to the 0, then this is e to the 0 p plus q n minus 1 plus this is e to the 0 times n minus 1, and this is e to the 0 p plus q whole power n minus 2 times e to the 0 p. That's it. Now simplify this, np, then this is 1 and that also 1, so 1 plus, in this term is, this is 1, so n minus 1 times that is 1 times p. Okay, so this is going to be np times 1 plus np minus p, np minus p plus 1. So np, let me rewrite again, 1 minus p plus np, I can write like this, then 1 minus p is given by q, 1 minus p is nothing but q, so therefore this is np times q plus np, so npq plus n squared p squared. So this is the second order moment of the binomial random variable. Binomial random variable. Now what is the variance? Variance of x equal to expected value of x squared minus the mean of the random variable and square it. So this is npq plus n squared p squared minus e of x is p np the whole squared, and this and that will get cancelled, then you will end up with npq. So this is your variance of the binomial distribution. So in this way we can calculate first order moment, second order moment, and from first and second order moments we can find the variance of the random variable. As I already said, the first order moment is the mean of the random variable, and mu2 minus mu1 squared is variance of the random variable. That's it. Now let me take one more example. Let's say exponential random variable. So exponential random variable, it is a continuous time random variable. So it is described by density of function, which is lambda times e to the minus lambda x, where lambda is non-negative, so it is greater than or equal to 0. Now for this random variable we already found its moment generating function. So mx of s equal to lambda over lambda minus s. Now take the first derivative of this m prime of s with respect to s. So this is u by v formula. So if you differentiate once, then lambda divided by lambda minus s the whole squared. Okay, so now substitute m s equal to 0, m s equal to 0, therefore this is lambda over lambda squared, which is 1 over lambda. Similarly, take the second derivative m double prime of s with suffix x, which is if you differentiate one more time, 2 lambda over lambda minus s whole cube. You do the derivation, it's simple exercise. So then substitute s equal to 0. This is 2 lambda over lambda minus 0 whole cube means lambda cube. This is 2 over lambda squared. So the second order moment is e of squared equal to 2 over lambda squared, and the first order moment e of x is equal to 1 over lambda. Now what is the variance of the exponential random variable? Variance of x equal to the second order moment minus square of the first order moment. The second order moment is 2 over lambda square minus first order moment is 1 by lambda square it, 1 over lambda square. So 2 by lambda square minus 1 over lambda square is equal to 1 over lambda squared. So this is variance of x. So in this lecture I have worked out some problem based on your moment generating function. So mgf is given. So using mgf we found the first order moment, second order moment, and first order moment is nothing but mean of the random variable, and using second order and first order moment we calculated variance of x. Okay, so variance of x is second order moment, that is mu2, first order moment mu1 squared. That's all. Okay, let me stop at this point. Thank you very much.